So last time we started talking about free radical chemistry, right? What is a free radical? Pardon? Something with a lone electron, that's right, or what we would call a free spin. Right? What might it look like on carbon? If I was to draw and give the three-dimensional structure of a carbon-centered free radical, what might it look like? A carbon with a dot? Does that account for it? What does it look like? Is it tetrahedral? Is it planar? Is it linear? Is it charged? Is it not? Trigonal sounds good. So if I have a carbon atom, right, how many other things are typically attached to a radical? 3, right? So we might have, let's just make it a methyl radical out of simplicity, right? Might be something like that. And then where's the electron going to reside? Well, I can put a dot anywhere, but it has to reside in an orbital. What orbital is it going to reside in? Okay, well, what is it? What do you think? It's a p orbital. Yeah, it's going to reside in a p orbital, and it looks like an sp2 hybridized carbon, right? That's kind of what we typically think of a radical as looking like. Now, they can take on different shapes and a little bit different hybridizations, but in general, this radical would have that structure. We would have an electron-rich or an electron-deficient carbon. It's electron-deficient. What's the formal charge? It's 0. And why is it 0? Right, it comes in with how many valence? 4, and how many does it formally own? 4. 1, 2, 3, and 4, right? So it is overall neutral in charge. Radicals can be charged. You can have radical cations and radical anions, but those are topics for more advanced classes, okay? But for the most part, the carbon radicals that we're going to be dealing with in this chapter are neutral in charge, so they're 0 in their formal charge, right? So, is carbon the only thing that we can have as a free radical? What else exists in this room right now that is a free radical? Oxygen, and it's a single radical or a diradical? It's a diradical, and so each one of the oxygen atoms bears a single unpaired electron, right? And you might think, well, why don't those things just pair up and form a double bond? The reason is molecular orbital theory, right? And those two electrons are sitting in what are known as degenerate orbitals of the same energy level. And so remember, you have to fill up energy levels half before you go back and double up, right? That's the reason why oxygen does not exist as a oxygen double bound to another oxygen, at least as we breathe it in air, okay? That's not how it exists, okay? So that exists as a diradical. Now, we started talking a little bit about this idea of halogenation of alkanes using free radical chemistry, and it turns out to be one of the important industrial reactions that we can do on pure hydrocarbons. So, for example, if we take ethane and we mix it with chlorine and we initiate the reaction, we will get chloroethane as one of the products. We can get further halogenation of the molecule as well. But if we just take this simple reaction and look at it, we know that we're going to have to break this carbon-hydrogen bond and get a carbon-centered radical, okay? And that's going to take 98 kcals per mole of energy to break that carbon-hydrogen bond. We can get that from the chart. We know that we're going to get some energy back in the sense that HCl is going to form a bond, and that's going to release energy, right? And that releases a negative 103 kcals per mole. And so overall, this process is exothermic by 5 kilocalories per mole. And then this free radical that we generate here will react with our chlorine and give us the product that we want plus a chlorine radical, which comes back up here. And we'll talk about that mechanism here in just a minute. And when we add all this stuff up, we find out that this process is exothermic by about 28 kilocalories per mole, meaning that the products are lower in energy than the starting materials, right? And so this reaction goes is favorable, and it goes to the right. Okay, so we can do this chemistry pretty easily. Now, there are three things that I want you to remember absolutely from this chapter. And that is all free radical reactions have three steps. Three elementary steps, I should say. You can actually have millions of steps. Okay? But you have three elementary steps. You have initiation, you have propagation, and you have termination. Okay? So repeat those for me. And termination. That's exactly right. And you need to be able to identify an initiation step, a propagation step, and a termination step. Okay? From here on out. Now, if we look at the initiation step that I have written up here, so this is for the free radical halogenation of ethane that we just looked at. What can you tell me about the initiation step that we see here? No radicals, and we go to radicals. So anytime you have no radicals on the left and radicals on the right of the equation, that's going to be an initiation step. Okay? And typically it's going to be involving one of the weaker bonds. Chlorine-chlorine bond's fairly weak. Okay? And so we take molecular chlorine, we shine a bright light on it, or we heat the heck out of it, and we can cleave that chlorine-chlorine single bond in what kind of fashion? Homolytic or heterolytic? Homolytic, that's right. Each chlorine atom gets an electron and we form chlorine radicals. We have just initiated the reaction. We now have free radicals to do the chemistry. Now we move down into propagation, and notice there are two propagation steps. You can have multiple propagation steps in a free radical reaction, but the rudimentary or elementary step is the propagation. What can you tell me? Let's just look at this first one right here. What can you tell me about a propagation step? You have radicals on both sides. That's exactly right. So if you have a step that starts with a radical and ends with a different radical, that's going to be a propagation step. And you can have multiple propagation steps in a mechanism. Okay? So for example, we just generated chlorine radicals. Those chlorine radicals now want to react with something, so they're in a solution of ethane. Okay? And so this chlorine atom is going to abstract what? What is it abstracting from the molecule? Well, okay, it's abstracting a hydrogen atom, which is really a proton and an electron, right? That's what it's doing. And so if we look at this, right, we have three arrows indicating, what are these two arrows indicating right here? The formation of a bond between chlorine and hydrogen, and what are these indicating? The breaking of the carbon-hydrogen bond. Very good, right? And so we're forming HCl as a byproduct, and we're forming a carbon radical. So we start with a radical, we end with a radical in this step. That's a propagation step. However, there's more than one propagation step. And now what happens is the ethyl radical reacts with the molecular chlorine that's around. Okay? So describe for me what these arrows are saying here. How about these arrows? A bond between what? Between carbon and chlorine. So we're going to form a bond between this carbon and this chlorine, right? We're also breaking a bond, the chlorine-chlorine bond, right? And so we just formed the product plus a chlorine radical. Now what happens with this chlorine radical? It goes back up into step one. And this propagation continues over and over again. Okay? You can have millions of these propagation steps, or billions. Okay? The number's huge. Okay? But at some point, we're going to start to run out of reactants, right? Nathan comes in and he puts only so much ethane and chlorine in the flask and starts the reaction. The propagation steps will continue as long as I have plenty of starting materials. But as the reaction proceeds, that eventually gets depleted. Okay? Once that gets depleted, then what step do we move into? We start to move into termination. And how would you describe termination? Okay, but how would you describe it in terms of the radicals? Right, radicals on the left, no radicals on the right. We're forming sigma bonds, right? So two chlorine radicals could come together and form chlorine. Two ethyl radicals could come together and form butane. A chlorine radical and an ethyl radical could come together and form the product. Okay? But what's happening is we're removing radicals from the reaction mixture, and we're terminating the process. Okay? The chain reaction is coming to an end. Okay? These are known as free radical chain mechanisms when you have initiation, propagation, and termination. Can anybody tell me what the concentration of free radicals are in this reaction at any given moment during the propagation step? What do you think? What is it approximately? Half? Real high. That's right. It's essentially nothing. It's zero. The radical concentration during the propagation steps is essentially zero. Because once you form a radical, it's so reactive it reacts. They don't hang around very long. So the approximate concentration of radicals at any given moment, as long as I have plenty of starting materials, is going to be approximately zero. So if the concentration of radicals is approximately zero, what are the chances of two radicals coming together to react with one another approximately? Zero. That's right. So that's why we always see in the propagation steps a radical reacting with something that has an octet. However, Terry, when we get to the point where we're starting to run out of starting materials, what happens to my radical concentration all of a sudden? We're in the propagation steps and it's approximately zero, and now all the ethane and chlorine is almost gone. What happens to my radical concentrations all of a sudden? They skyrocket. Okay? Boom, now all of a sudden we got tons of radicals around. Now what are the odds of two radicals coming together? Higher, right? It goes up. And so termination steps only start to take place when the concentration of radicals increase, okay? And that's when it starts to stop the process. There is a lot of math that can go behind this, and for those of you in polymer science, when you get into the higher level polymer classes and you start talking about this, you'll start deriving equations to figure out what your chain steps are and your molecular weight distributions are and all this good stuff. But it's based on kinetics and the fact that radicals concentrations are essentially zero at certain points, et cetera, okay? So there's a lot of stuff that goes into that, all right? You need to be able to identify an initiation step, you need to be able to identify propagation steps, and you need to be able to identify termination steps. This mechanism is not hard, but there's a lot of steps to it, right? There's a lot of steps to these free radical mechanisms. And so we've got these steps that we need to go through. Okay? Let's look at some problems from the ACS study guide. Which of the indicated sites would most readily undergo hydrogen atom abstraction to generate a radical? Number 4?
Probably not one of those because it would be a primary radical and those on the stable.
Okay. What else could we have? Who does that? Who thinks 2? 2 or 3? The answer is 2. Well, tell me why. Okay, very good. If we remove the hydrogen at this position, we would end up with a tertiary radical. However, that's the same as if I remove from 3. So that in and of itself is not sufficient. And so what does that have to do with it? Why? Resonance. That's exactly right. If I remove the hydrogen here, I end up with a radical that is resonance stabilized, right? So if I draw them out, let's see, there, right? And there. I can draw resonance structures for this one. How would I draw resonance structures for that one? Okay, that's right. So I'm going to push that electron there, and that electron there, which effectively moves the double bond here, and the radical. So I have those resonance structures that I can draw, right? Well, I can also draw resonance structures if I remove the hydrogen here, right? So why is this not number one? It would be primary, right? And so here I have a tertiary that is resonance stabilized to another tertiary. Pretty stable, right? Now, rank those for me, 1 through 4, from most stable to least stable. Well, we just determined the most stable, right? Is 2. 2 is greater than what? 3? I'm talking about stability. 2 is the most stable. It's tertiary and it's resonance. 3 because it's tertiary. But what about 4 because of resonance?
Doesn't tertiary trump resonance?
You sure about that? Resonance is pretty good, right? I'd actually say 4, and it's going to be pretty close to 3, but it'll be slightly better, and then what? 1. Right? Resonance structures almost always trump. Remember in carbocations when we had a lot of resonance structures even though it looked like it might be primary? Right? Each of these reactions occurs during the free radical chlorination of methane. Which step corresponds to the first propagation step of the reaction? Read that again. The first propagation step. So what can we eliminate?
A.
We can eliminate A because it ain't a propagation. It's a what? It's an initiation. And what else can we eliminate? B because it's a termination. All right. So you just went, because you know the difference between initiation, propagation, and termination, you went from a 1 in 4 chance at the end of the exam to a 50-50. Okay? Now, which step corresponds to the first propagation step of the reaction?
Because it's only methane.
That's right, because the first propagation step, remember those chlorine radicals are coming into that first propagation step to react with the hydrocarbon, right? And that's happening here in C. This would be which propagation step? The second propagation step, right? Very good. All right, so we're going to continue talking about free radical halogenation. And we're going to talk a little bit about the fact that bromine is actually very selective. And we'll, if we have time, we'll get into oxidation and polymerization a little bit. Okay? I don't spend as much time on the polymerization because we have a whole building across the way that teaches all that kind of stuff, and you're more than welcome to take a class over there. So I won't steal their thunder. So let's look and see what we've got here. We know that the initiation step involves the creation of radicals, right? So for example, chlorine, use UV light or heat, we generate chlorine radicals. Those chlorine radicals then enter into the propagation step. This is the free radical halogenation of methane or natural gas. We end up with a methyl radical plus HCl. Now what happens to that methyl radical? What does it do? Pardon? You were right, I think. That's right. So now it reacts in the second propagation step with chlorine. We end up with the product. And now what happens to the chlorine radical we just generated? Goes back up into propagation step number 1. And this continues as long as we have what around? As long as we have starting materials around, right? We're going to continue to do our propagation. But at some point that ends up being depleted, and we enter into what? The termination steps, right? And we can have multiple termination steps. You can have a chlorine radical and a carbon radical come together to form what looks like product. Actually, it is product. Some of the product gets formed by termination. What else is a possibility? 2 chlorines coming together. Well, okay. I got them a little out of order. 2 methyl radicals coming together, right, to form ethane. And then, of course, the 2 chlorine radicals coming together to form molecular chlorine. Now, all of these, this you won't be able to tell because that's actually one of the products from propagation. But these will only be available in small quantities at the very end. You'd have to use very careful gas chromatographic analysis to detect them, okay? But in fact, you can detect them, and they are products of termination, okay? So let's repeat them again, the 3 steps. Initiation, and we know that because there is no radicals on the left, radicals on the right. Propagation, radicals on both sides, kind of like Congress, right? And then termination. Radicals on the left, no radicals on the right, right? Very good. All right. So we can add up all this stuff. We're really not going to have you doing much of this type of math anyway in here, right? You can do up all the additions, and what you'll be able to determine then is the energy of activations experimentally and by using a bunch of this stuff, okay? Now, it turns out that the transition state in chlorinations is much lower than the transition state for brominations. What does that tell me about the stability of the chlorine radical versus the stability of the bromine radical? Chlorine is a lot less stable. It's higher in energy, right? That's why, since this is higher in energy, that's why this distance is smaller, right? Okay, what about the bromine? It's much more stable, right? So what does that tell us about the selectivity? Which one's going to be more selective? Chlorinations or brominations? Brominations. And it turns out that brominations, free radical brominations, on a laboratory scale are kind of practical. We can go into the laboratory and do free radical halogenations using bromine sources and do some selective work and end up with a product that we want. Chlorinations are not really practical on a laboratory scale because chlorine, number one, is a gas, and 2, it's not very selective. It will react with just about anything that it can react with. Bromine's a little more picky, and that turns out to be pretty nice for us, okay? So, and you can tell it's quite a bit different, right? If we look at the energy of activation, 78 kcals per mole versus kilojoules, not kcals, versus 16 kilojoules per mole. So bromine is actually quite selective in how it reacts, okay? Now, we know that this is the order of reactivity in halogenation. Fluorine is very, very reactive. In fact, so reactive it's not practical, right? What does it typically do? Kaboom. That's right. So we're really stuck with chlorinations and brominations. Iodine really doesn't react very well at all. There's a lot of chemistry out there being studied about how to do chemistry of iodine, because it turns out that iodine doesn't really like to add to double bonds. It doesn't like to do halogenation reactions of alkanes, etc. So ways in which you can get that to work are currently being sought after. Okay? So if we look at all the numbers, this first step, which is what kind of step? Is an initiation step. We can see that fluorine, right? Not too bad. Iodine, oh, that's actually better, right? We can generate iodine radicals pretty easy. It seems like we should be able to do this, right? Chlorine and bromine are kind of up here, right? Is this endothermic or exothermic? Does that make sense?
Yes, you're adding energy in.
Well, that's true, but I'm breaking bonds, that's right. And all bond breaking events are endothermic, right? Regardless of what my biochemistry friends tell you, okay? All bond breaking events are endothermic, okay? Now, if we have the halogen come in and react with methane to give a methyl radical, we can see what's going on here, right? This is very what?
Exothermic.
Very exothermic, and so kaboom, right. This is slightly endothermic. This is fairly endothermic, right? And this is very endothermic, right? So this is starting to account for why we're not getting the chemistry to occur with iodine. Then in the second propagation step, right, we've got the methyl radical reacting with the free halogen, and now we can see a lot of energy coming out, right? And really understand why this goes kaboom. And here we've got exothermic processes, okay, that aren't quite as high as with the fluorine. What do I want you to take from all those numbers? Fluorine's greater than chlorine, greater than bromine, much, much greater than iodine. That's what I want you to take home from it, okay? But this order comes out of this math that you all did when you were in general chemistry. Okay, this is the kind of stuff that you all did in Gen Chem when you were talking about energetics and equilibria and all that kind of stuff. Okay? Now let's look at the chlorination of propane. Propane has two types of hydrogen. What are they?
1 to 3, 2 to 3 hydrogens and 1 to 2 hydrogens.
Okay, and what do we call those? We have primary hydrogens and we have secondary hydrogens, right? So we have how many primary hydrogens? Primary? We have 6. And how many secondaries? 2, right? So we have 3 here that are primary, 3 here, so a total of 6 to 2, or a 3 to 1 ratio, right? And we know that chlorine's not very selective, so it can abstract both primaries and secondaries. So based solely on statistical probability, what would you expect the reaction products to be, and what would the ratio be?
We have a lot more with chlorine at the end.
Okay, so 1 chloropropane versus 2 chloropropane, right? You would predict that you would have more 1 chloropropane than 2 chloropropane, right? And what you find ain't the case. It's nearly 1 to 1, using rough math like I like to use, right? But if you're a little more quantitative, you actually find that you have less 1 chloropropane than 2 chloropropane. But we just figured out that we had a 3 to 1 statistical factor, right? The odds of that chlorine radical bumping into a primary hydrogen to abstract it is 3 times greater than bumping into a secondary hydrogen, right? So why am I not seeing the primary, or the 1 chloropropane being the major product? Stability of what?
Well, the carbons on the ends are going to be like holding on to the hydrogens a little bit tighter
Okay.
than the one in the middle.
Stability has something to do with it, but stability of what? The free radical intermediate that we get, right? So what does this tell us? It tells us that not all hydrogens are created equal, are they? Not at all. And remember back in chapter 2 or 3, whenever it was that we were going through hydrocarbons, probably chapter 3, or maybe 4. I told you had to be able to identify the types of carbon and the types of hydrogen, and that was going to be important. It's important now, right? Secondary hydrogens are more or less reactive than primary by this data. More. They are more reactive than primary. And we can actually calculate with this data, we can calculate the relative reactivity of these different types of hydrogen, just using a little basic algebra, okay? We would have predicted that 1 chloropropane would have been 3 times more concentrated in the product solution than the 2 chloropropane. We would have expected a 3 to 1 ratio, just based on probability. But probability doesn't take into account the reactivity differences, right? And so we have to fudge the data a little bit here to get that. We can calculate what this is, okay? So let's look at it. Again, we've got propane. Jamie Lou came in and took propane, chlorine. She put a bright light on it for a while. She got her products. She went and did gas chromatography, and she found out that 1 chloropropane is 45% of the mixture, and 2 chloropropane is 55% of the mixture. She now has everything she needs to do to figure out the reactivity differences between a primary hydrogen and a secondary hydrogen in the free radical chlorination, okay, of a simple hydrocarbon, okay? And it turns out it's 3.6 times more reactive than a primary. So how did she calculate this? Well, she knows the product mixture, and she defines it as 2 chloropropane over 1 chloropropane. Why 2 chloropropane over 1 chloropropane? Why not the reverse? That's right. You typically want to deal, you could have done it the other way, but we know that this has to be more reactive, right? So we're going to put that on top. And that's equal to the product mixture, 55 to 45, right? She figured that out from her gas chromatography by measuring the peak areas. And she also knows that that's equal to some statistical factor times the reactivity of the secondary hydrogen over the reactivity of the primary hydrogen, right? Well, we know the statistical factor, right? What is that? 3 to 1, or actually 1 to 3 in this case, because we have it, how we have it figured out, right? So the product mixture was 55 to 45. There are 2 secondaries for 6 primaries, so that's a 1 to 3 ratio, right? 1 because 2 chloropropanes on the top, 3 because 1 chloropropane is on the bottom, right? Times the relative reactivity of secondary hydrogens over primary, right? And so now all she has to do is a little bit of algebra, and the number comes out to be 3.6 to 1. So that tells her that the reactivity of a secondary hydrogen is 3.6 times more reactive than the primary hydrogens in propane in the free radical chlorination. Is that true of all free radical reactions on propane? No, only in the chlorination. These are empirical numbers that you get from experiment. You can't say that a secondary hydrogen is 3.6 times more reactive in the free radical bromination. It's only 3.6 times more reactive in the chlorination reaction. I can promise you that there will be at least one problem on the exam where you have to do this math. Okay? It's not hard math. It's a heck of a lot easier than anything you ever had to do in Gen Chem in terms of the math, right? So all you need to be able to do is identify the types of hydrogens, be able to count them so that you can get the proper statistical ratio. And I will tell you this, that is where most students mess this problem up. They can't count to 6 or 7, okay? So don't make that mistake. Make sure when you're doing it, you accurately account for all of your hydrogens, okay? All right, let's look at isobutane. What kinds of hydrogens do we have here? Okay, we have tertiary and we have what?
Primary.
And we have primary. And what's the statistical factor? 1 to 9. That's right, because we have 3 on each one of these methyl groups, right? And they're all primaries. They're all identical. So it's 1 to 9. Right? And Gabby comes in, she takes isobutane, she takes chlorine, she shines a bright light on it, and she gets these 2 products. And she goes and runs GC, and she finds out that she has 63% isobutyl chloride and only 37% tert butyl chloride, and now she wants to know the relative reactivity of primary versus tertiary, right? So she does the same thing. We know it's a 9 to 1 statistical factor. She knows this ratio, the tert butyl chloride to isobutyl chloride is 37 to 63. Okay? Again, you can have it either way you want as long as you keep track of what you're doing. The statistical factor, right, is we've got 1 tertiary hydrogen for every 9 primary hydrogens. She knows that that's going to be also times the relative reactivity. Does a little bit of algebra, and she finds out that it's 5.3 to 1. So we know that a tertiary hydrogen in a free radical halogenation is 5.3 times more reactive than a primary, right? So a tertiary is 5.3 times more reactive in this chlorination reaction than the primaries. If that's the case, why is it that the tert butyl chloride wasn't the major product?
Because
It's still 1 to 9. That's right. Even though it's a lot more, it's 5 times more reactive than the primaries, you still have 9 times the number of primary hydrogens, right? So statistics is still in favor of forming isobutyl chloride. You would have predicted this ratio to be a lot less tert butyl chloride. You would have expected 9 to 1, right? If this was just purely statistics and the reactivity didn't come into play. Okay. Now brominations, little different story. So I have Paige come into the lab, and she takes isobutane, the same stuff that Gabby used. But instead of using gas, chlorine, she comes in and she pours in some liquid bromine, and she shines a bright light on it, heats it up a little bit because it's kind of slow to go. And then she takes the products and she goes and runs the analysis, right? And she goes and runs an analysis. Let's say she's using gas chromatography. And she finds just a little tiny blip and then a huge peak for the tert-butyl bromide. So it's greater than 99%. Okay? The selectivity here is going to have to be estimated because this little tiny blip that she has for this is hard to integrate, right? It's hard to get a good number for. So we're going to make an assumption. What kind of assumption will we make? Can we do the math with a 0 in the denominator? Use something small, right? But we typically like to be fairly conservative with this. And so what we will do is we'll say, okay, let's make it 99 to 1. That'll give us a lower limit, okay? And so now we can do the math. We're assuming that we have 1% of this, even though it's really just a trace. That's going to give us kind of a rough figure, right? So we know that we have a 99 to 1 mixture. We know the statistical factor, which is 1 to 9. We know the reactivity. We do a little bit of algebra. And what she finds out is that that tertiary hydrogen is 891, at least 891 times more reactive than those primary hydrogens, right? Why is that? Why all of a sudden is the reactivity of the tertiary not 5.3? Why is it 891 now? Okay, but why? That's true, but why?
Bromine is a lot more stable than chlorine, so we can sit around and wait for it on this perfect hydrogen.
Okay, yeah, that's essentially right. It's so stable that it's only going to react with the weakest bond, right? It's not reactive enough just to pluck off any hydrogen. It's going to bump into those primary hydrogens every now and then, but not much of a reaction is going to occur. Every now and then one will. But when it bumps into that tertiary hydrogen, right, chemistry is going to occur. And so you find that the reactivity in the brominations is much, much, much better, right? And so when Gabby did her experiment, let's go back, right? She ended up with essentially a 2 to 1 mixture of products. Let's do math, government math here, right? About a 2 to 1 ratio. What's Gabby going to have to do? Cry? What? Oh, separate it. That's right. You're going to have to find some way to separate the product that you want. And if you wanted the, let's say, the isobutyl chloride, you're going to have to find a way to separate the isobutyl chloride from the tert-butyl chloride. You're going to have to do some type of chromatography probably, or distillation, right? What's Paige going to have to do? Not a thing. Not a thing. She just gets the product that she wants because it's essentially all tert-butyl chloride, or butyl bromide, excuse me. Huh? Well, but the nice thing is, what have we been using alkyl halides for? What kind of chemistry have we been using alkyl halides for? What do you think, Rose? We've been using them for SN2 reactions. Okay, that's one thing. What else have we been using them for? Eliminations. Not addition. We've been doing additions to make alkyl halides. That's true. Right? And in all of those cases, what is the halogen? A leaving group. So do we care if it's a bromine or a chlorine? Not a bit. Right? So I'd much rather have a bromine for a couple of reasons. One, it's more reactive in these reactions anyway, and it's more selective. Right? So I can get the products that I need more selectively, minimize my chromatography, and then I'm going to take it on and do some type of either SN1, SN2 chemistry, or some type of elimination and get the products that I want, right? All right. Now, let's look at pentane. What types of hydrogen do we have on pentane? We have primary and secondary, right? Will everybody agree that pentane is not chiral? You agree with that? Why do you agree with that? Okay, it's symmetrical right? We got mirror symmetry and all that good stuff. There is no carbon atom on there that has 4 different substituents, right? Okay. Now, when we do free radical chlorination, we're going to end up with a few products. We're going to end up with 1-chloropentane by removal of which hydrogen? A primary hydrogen, either this methyl group or this methyl group, right? We're going to end up with 2-chloropentane, which is going to be removal of a secondary hydrogen from the number 2 carbon, or this number 2 carbon, which are identical, right? 2-chloropentane is chiral. Will everybody agree with that? Where's the chiral center? The carbon containing the chlorine, right? It contains a hydrogen, it contains a chlorine, it contains a methyl group, and it's attached to a propyl group, right? 4 different things. So that's going to be a chiral center. And then we're going to end up with 3-chloropentane, part of the product mixture, right? And that's going to be achiral because it's got a hydrogen, a chlorine, and 2 ethyl groups, which does give symmetry. That's exactly right. All right. So out of this reaction, we're going to end up with 2-chloropentane as part of the mixture that's going to be chiral. So Jamie Lou is going to take the mixture. She's going to put it in a polarimeter tube. She's going to go down to my lab and use my polarimeter, my $15,000 polarimeter, and what's she going to notice in terms of how it rotates plane polarized light? It doesn't. And why doesn't it? Because it's a racemic. Now, why is it racemic? It is a 50-50 mix, that's right, but why is it 50-50? The chlorine doesn't care. You're really close. It doesn't have a heart. It's not the Tin Man, huh? Well, that's true. That's true, too. Yeah.
Isn't it only sigma bonds and
They are sigma bonds. They can rotate around like that, but they can't, you're not going to invert from R to S. What's the shape of that free radical intermediate? Not linear. Trigonal, planar. That's right, and that's why we end up with a racemic mixture. Okay, we're going to get 2-chloropentane in racemic form because remember what's going to happen is the chlorine radical is going to abstract one of these secondary hydrogens, right? And we're going to end up with a trigonal planar free radical intermediate. Of course, I'm not showing the HCl that's formed, but you know that that gets formed, right? Now, this is what happens in what step? Nope. This is propagation, right? Remember, initiation is the generation of the chlorine radicals. But now we have this reacting with a chlorine radical to give a radical. So we got radicals on the left, we have radicals on the right. So it's a propagation step. Do I have another propagation step? What do you think, Harrison? Will we have another propagation step?
Yeah, we'll do the second step.
Absolutely. This is going to react with the chlorine, right? With the second stuff, that's right. And if the chlorine gets attacked from one face, you end up with the S enantiomer. And if it gets attacked from the other face, you get the R enantiomer. Remember, this radical doesn't mean that it's only in this top lobe, right? It's actually in both lobes. It's just never in the middle, right? And so what are the odds of the chlorine coming in from the top or the bottom? They are exactly 50-50. And so when Jamie Lou goes and runs the polarimetry experiment, she's got just as many of these molecules as she has these molecules, and it cancels each other out, and you see zero rotation, right? All right. So that's why we end up with a racemic mixture when we generate chiral centers through these free radical reactions. If, and only if, the starting material is achiral. Is that always the case? No. Okay? Now, if we start off with S2-chloropentane, so we already have a chiral center here. Okay, so Terry just went and spent $250 for a gram of this, okay, to do this experiment. And she takes this. It's already got a chiral center, right? And now she's going to do the free radical halogenation on this. and she's going to remove one of these other secondary hydrogens, okay? Is the top face of this radical intermediate equivalent to the bottom face now?
No.
Why not?
You got that other chlorine up all in it, one nose stays.
Up all in it. Okay, I like that. That's right. It's all up in its business, isn't it? That's right. And so the top face is no longer equivalent to the bottom face. And so we would predict, right, that we might have some facial selectivity because one side is more crowded than the other, right? Now,
Chlorine doesn't want the other chlorine to steal its place.
okay, so if we have the chlorine attacking the radical from one side, we haven't messed with this chiral center at all, right? So it was 2s, so it's going to be 2s here. And we can have 2s, 3s, 2,3-dichloropentane, or we can have 2s, 3r dichloropentane. Now, how are these related to one another? Are they enantiomers? Pardon? They are diastereomers. That is correct. And what do we know about diastereomers? They have different chemical and physical properties, and they also have different activation energies to formation. So the energy of activation to form this one is either going to be higher or lower than the energy of activation to form this diastereomer. And so would we expect them to be generated in equal amounts? No, not at all. They may be really close, and that's hard to predict, but they do not have to have the same, and will actually end up forming the